Okay, so the first thing on your exam is going to be about types of elements. So just make sure you guys have your periodic table out. We talked about this a while ago, but just to kind of make it very brief, there are 3 types of elements on the periodic table. The first are called metals. The second is called nonmetals. And the third are called metalloids. Okay, metals, nonmetals, and metalloids. Okay. And I'm not going to be asking you these explicit questions on the exam, but you'll need it for the next type of problem we're going to do. So just make sure you're aware of how to differentiate between them. Metals are very easy to find. It's most of the periodic table. It's pretty much everything on the left, the middle, and the bottom. Okay, so you guys don't need to color it on your periodic table or whatnot, but it starts at lithium, and basically it's the entire left side, the entire middle, the entire bottom. And we talked about that line that separates the most common ion. It also includes some of the elements down here as well. Okay, but I'm not going to really ask you anything about stuff down here. Just know that left, middle, bottom, and you should be good. And a lot of them, they're names that you guys are familiar with, right? So things like calcium, nickel, iron, you can know that those things are metals to begin with. And so shouldn't be too hard to find, but those are metals, left, middle, bottom. Okay, the next type are called nonmetals, and these are the ones that are on the right side of the periodic table. So typically you're going to want to think of it from carbon, and then it's going to be the ones that have like negative most common ions, like phosphorus, and then bromine and things like that. You don't need to memorize them exactly. The ones that you really need to know are just going to be these 6 right here. Okay, these 6, and then the right side column. Okay, so nonmetals typically on the right side. And again, I'm not going to be asking you explicitly is this a metal or non-metal. Just be aware of generally where they are. Okay. All right, and then the last one, metalloids. I'm not going to ask you about this at all on the exam, so you don't need to commit this to memory. But we talked about this before. But it's basically this little staircase that separates the metals and the non-metals. It's going to be like right here. But again, you guys don't need to be very aware of the metalloids. All right, so those are the 3 types of elements on the periodic table. An easy way to think about it is that metals, they have positive most common ions. They like to make a plus charge, so +1, +2, +3, so on and so forth. The only exception is hydrogen. Hydrogen wants to become +1, but hydrogen is a non-metal. Okay, so if you think of like hydrogen gas, right, doesn't really have any metallic properties that we're familiar with. So just remember, hydrogen is the weird one. This is a non-metal, even though it's on the left side. Okay, and then for nonmetals, easy way to remember it is that they form negative most common ions. Okay, so very easy way to differentiate between the two. And I say this is the way that you can solve the problems that will actually be on your exam. Okay. The types of questions that involve this are going to be this right here. Okay, so you're going to look at these compounds and determine if they are ionic or covalent. And we talked about this at the beginning of the year. But ionic compounds are made out of ions. They're made out of 2 elements that have, one of them, their most common ion is positive, and one of their most common ions is negative. Okay, so it's made out of something that has a positive and negative that come together. Okay, another way you could think of it is made out of a metal and a non-metal. Okay, whatever makes more sense to your brain. Both ways of figuring out is valid. And then covalent, these are ones that are made of nonmetals only. Okay, easy way to think about it is that they're going to be made of things that are negative and negative, the most common ions at least. Okay, so we're going to look at a couple examples just so you guys see what I mean, but it's pretty simple. Let's look at part A from number 2, Rb2s. If you take a look at it, there are two elements that make up Rb2s, right? It's made out of Rb and it's made out of S. So we're going to figure out, is it ionic or covalent? So let's take a look at Rb on our periodic tables. If you guys take a look at Rb, what is Rb's most common ion going to be? It's right here, 37. Is going to be positive or negative? Yeah, positive 1, right? It's in the +1 column. So Rb wants to be Rb plus 1. The other one is S. What does S want to become? Yeah, -2. So you got a positive and a negative, so that means it's going to be an ionic compound. So that's pretty much how you do it. Pretty simple. Just figure out what the most common ions are. Yeah. Covalent, if it's made out of two elements that have negative most common ions. Yeah. Yeah. So we're gonna look at one right now. So we'll just jump right into that. The example on the review is NH3. Actually, that's a bad example because H is a nonmetal. Okay. Let's look at H2O. Actually, not H either. My bad. Let's look at CO2. Okay, CO2. CO2 is made out of carbon, right? Carbon wants to become -4. Oxygen wants to be -2. So 2 negative ones, so that's going to be covalent. And again, the exception is going to be the ones that have hydrogen. So water, H2O, it has hydrogen, which is a nonmetal. O wants to be -2, so this is also going to be covalent. Okay, so just keep that in mind. Hydrogen is the one that kind of messes up that pattern, but that's how you can determine ionic covalent. Okay, so you'll have one question like that on your exam May 4th. Okay, so let's review ionization energy. I am going to abbreviate it as just IE. So IE. And ionization energy is very simple. Okay, it's the energy required to remove an electron. Okay. Okay, so it's the energy required to remove an electron from the atom. Okay, and I'm gonna be going over, I'm gonna kind of explain a lot right now just so that you guys have a lot of different ways to think about it, depending on how your brain works and how it understands it. Okay, but if you have a greater ionization energy, it's harder to remove the electron. Okay, so the bigger the ionization energy, it's hard to remove it. It takes more energy to remove the electron. So think of ionization energy as how much energy you need to put into taking it out. Okay? Okay, and then the reverse is true as well. If it has a lower ionization energy, it is easier to remove the electron. All right, so let's talk about greater ionization energy. If it is harder to remove the electron from the atom, is it more attracted to the atom or less attracted? Yeah, it is more attracted. Okay, so just keep that in mind. If it is a greater ionization energy, another way to think about it is how tightly is that electron attracted to the atom? And again, the reverse is true as well. If it's a lower ionization energy, it's less attracted to the atom. Okay. So hopefully that concept makes a little bit more sense. I'm going to go over how to solve the problems for it. That'll be on your exam. And then we'll move on to, I guess, the next part of ionization energy. All right, so ionization energy, it depends on three things. Okay, the first thing you want to look at, okay, so there are more shells. If there's more shells in an atom, is the electron less attracted or more attracted to the atom? If you are looking at somebody, right, and you're further away from them, are you going to be more attracted or less attracted? Less. Yes, less. Good. Hopefully that analogy makes sense. The more shells an atom has, the less attraction that electron will feel, right? Just like how if you're talking to somebody, the further away you are from them, the less attracted you will be to them. Okay, no matter how good looking that other person is. Okay, and then the reverse is true as well. The less shells there are, the more attraction there is because the electron is closer to the middle of the atom. All right, the next thing you want to look at are the protons. Okay, now if you remember, protons are positively charged. It's like a positive magnet, and electrons are negatively charged, right? So they're naturally attracted to each other. But if more protons, do you think that's going to result in more attraction or less attraction? Electrons and protons are attracted already. More protons is more positive energy, right? So if there's more protons, it's actually going to be more attraction. Because more positive energy in the middle of the atom. It's going to pull the electrons more tightly. Okay. So think of protons as kind of like the pull that the atom has. The more protons there are, the more it will attract the electron. And then the less there are, the less it will attract. Yeah.
Even if there's like a limited amount of electrons, even if like there's still like
well, shells matter more. So you want to look at the shells first. You only look at protons if there's the same number of shells. Yeah, so we'll do a couple of practice, just hopefully it answers your question. But yeah, always go shells and then look at the protons. All right, so let's do a couple problems on your review, and then we'll move on to the next topic for today, the last thing before the exam. Okay, so the ionization energy problems are at the very bottom, topic 5. So we're going to take a look at basically 2 elements, and we're going to determine which one has a greater ionization energy, okay? So we're going to look at lithium and beryllium. So I want you to take a minute on your periodic table, find lithium and beryllium, and I want you guys to first look at how many shells do they have. So on your paper, write down how many shells they have, lithium and beryllium. All right, guys, so if we take a look at lithium and beryllium, how many shells do they have? Lithium and beryllium, how many shells? 2. They both have 2 shells. Okay, so they both have 2 shells, so we got to look at a different criteria. We got to look at protons, right? If you look at lithium, how many protons does lithium have? 3. How many protons does beryllium have? 4. Good. Easy peasy. Okay, so if we were to draw this out, and you guys don't need to draw it, I just want to kind of help you visualize it. This is what lithium looks like. In the middle of the atom, there are 3 protons. Okay? It's going to have 2 shells. And then if you take a look at beryllium, it has 4 protons in the middle, and it has 2 shells. So the shells are the same, so we got to use protons. If you take a look at beryllium, beryllium has a stronger positive energy in the middle, right? So what it's going to do is it's actually going to pull the electrons in more tightly to the middle. And so it's actually going to hold on to the electrons more. So in terms of greater ionization energy, beryllium has a greater ionization energy. So beryllium has a higher ionization energy than lithium. Okay, and the reason why, first, it has the same number of shells, but it has more protons. Okay? If it has more protons, there is more attraction with the electron, and so it is harder to remove the electron. And that's why it has a higher ionization energy. Okay, God bless you. Okay, so same shells, but there's more protons. That means the electron is more tightly held, which means it is harder to remove because it takes more energy to remove the electron. Okay, so the ionization energy is higher. Okay, if the question asks which one has a lower ionization energy, what would the answer be? Yeah, lithium, because it's easier to remove the electron. Okay, so that's how you want to take a look at it. Alright, so for 24, we are comparing carbon and nitrogen. Okay, so before we pick our answer, we got to look at the shells, right? They both have 2 shells, so we can't use the shells. So the difference is going to be the protons, okay? Carbon has 6 protons, so if we drew a picture of carbon, it would have 6 protons in the middle, 2 shells, and then nitrogen would have 7 protons, 2 shells. And so which one do you think holds the electron more tightly? Carbon or nitrogen? Yeah, nitrogen. So nitrogen is going to hold it more because there's more positive energy in the middle. So that would be your answer. So for your answer, you would write nitrogen as your choice. And then you would say something along the lines of same shells, but more protons. Okay, since there's more protons, there is more attraction. And so that means it is harder to remove. Something along those lines. Okay, it doesn't need to be exactly word for word what I have written down, but as long as you refer to those things, you should be good. That it's more attracted to nitrogen than carbon. All right, so if we take a look at 25, I want you guys to jot this down in your notes, but 25, you are asked to compare sodium and sodium's most common ion, which is Na+, because it's in the +1 column right here. Okay, so for this problem, you got to be able to identify what the most common ion is. So if you don't know your most common ions, you can't really solve this problem. Okay, but sodium and sodium's most common ion, which is Na+, because it's in the +1 column. All right, so again, what we want to do is we want to start by figuring out how many shells they have. So let's start with sodium, Na. How many shells does Na have? 3. So we're going to draw 3 shells around it. Okay? And again, I know this is tedious. You don't have to do it when you're solving every problem, but I just want you guys to do this for your notes so that you guys have it to visualize. So it's going to have 3 shells. Okay, so I'll make a little note here. Regular sodium has 3 shells. Okay, so we're going to fill in the shells. So I'm going to just tell you, I'm not going to have you guys do any of the thinking, just to speed things up. But the first shell has 2 electrons. The second shell has 8 electrons. Okay, and then the last shell has 1 electron. And you can tell how many are in the last shell because sodium is in the first box on the first row. If it's in the first box, it's going to have 1 valence electron. Okay, so that's the shell model, and I'm sure that if you wanted to take your time on the exam and be really sure about your answer, you can draw it, but it's not a requirement. Okay, so we said that sodium, its most common ion is Na+. Okay, for this plus, does it mean you gain or lose an electron? Yeah, you lose an electron. So just keep that in mind. When it goes from sodium to sodium plus, you are going to lose 1 electron. Okay? All right, so if we take a look at Na right here, you see how there's 1 electron in the outside shell, right? So what's going to happen is you're going to get rid of that electron. Are there any electrons in the outside shell now? No, it's empty, which means that when sodium loses the electron, it's going to lose the third shell. It's going to lose the outside shell. So if you draw a picture of Na+, it's only going to have 2 shells. Okay, and we're not going to fill in the electrons. But the key thing to note is that there are 2 shells. Okay, and that's going to help answer your question, which one has a higher ionization energy. Okay. So if you take a look, regular Na, the electron is 3 shells away, so it's further away, whereas Na+, it's only 2 shells away, right? So that means which one has a greater ionization energy? it's going to be Na+. And the answer is very simple. It has less shells than Na. Okay, so that's going to be your answer for that one. I'd say that's the trickiest one because you need to identify first the most common ion and that it loses a shell, and that means it is held more tightly. I.e. 1. Okay. Okay, and first ionization energy is pretty simple. It's just the energy required to remove the first electron from an element. Okay, so if you got an element and you remove one electron, it's how much energy it takes. How much effort does it take to remove one electron? Okay, well, if there is a first, there's also a second. Okay, we refer to that as. Okay, so basically, how much energy does it take to remove another electron from the atom? Okay, so for example, you guys don't need to draw this because you already drew it on your paper. But we just talked about Na, right? And we said that Na had 3 shells with 1 electron on the outside. Okay, IE1, the first ionization energy is basically how much energy does it take to take away this 1 electron and make it Na+. Okay, and then we drew this right here. Okay, IE2, the second ionization energy is pretty simple. It's just how much energy does it take to remove another electron from that. So Na plus has 8 electrons in the second shell. Basically, how much energy does it take to remove one of those electrons? So to go, if you remove a second one, it'll become Na2 plus. It'll still have 2 shells, but the difference will be there will be 7 electrons on the second shell. Okay, so you kind of get the point. Basically, it's just you're just taking away another electron. And then the list goes on and on. You can also go IE3, which is the third one, IE4, so on and so forth. It's just how many electrons you're removing. Okay, so that is the general concept. But there's a lot of different questions that can come from this. Yeah. Use for the electrons? Yeah, so this happens a lot with ionic compounds. This is how ionic compounds become compounds. If you want to, I'll give a very brief overview. So Na wants to get rid of electrons, right? But then we know that there's elements that want to gain electrons, right? They're given to the ones that want to gain. Yeah, so like for example, chlorine, it wants to gain an electron. So sodium would give one to chlorine. Cl becomes Cl minus, which is what it wants to become. Yeah. And that's how salt is formed. Okay, so from that, we can actually derive a lot of different types of questions. So right now, I'm actually going to go to your assignment, and we're going to actually go over a couple of your assignment questions, just so you guys can get an idea of how what the types of questions will look like. All right, so number 2 on your assignment, let's take a look at it. This is what multiple ionization energy questions look like. So if you guys take a look at the problem, it tells you that you have magnesium's ionization energies. Okay, so we're looking at Mg. Okay, so I want you to take a second, go on your periodic table, just look at Mg, make a note of where Mg is. It's on the far left, 3rd row. So just make a note of where it is. Okay. And then the question is saying, explain this data. So you have this data right here about the ionization energies, and it's asking you, explain why the data is what it is. And you got to talk about their valence electrons, the outside electrons. Okay. And just to let you know, this is the type of questions that are on the AP test, AP Chem test, the stuff I give on the AP homework. So this will kind of give you a gauge on, hey, can I understand the types of questions that they cover in AP Chem? Okay. Okay, so let's look at IE1, 738 kilojoules per mole. Again, this is just a number telling you how much energy it takes to remove the electrons, okay? But before we do that, let's talk about what these numbers mean. If the IE number is bigger, is it easier to remove or harder to remove? If it's a bigger number, it's harder to remove. Okay, if you didn't know that, make sure you jot it down. The bigger the number for ionization energy, the harder it is to remove. Okay, because you need to use more energy to remove that electron. Okay, so if you have a bigger number, it is harder to remove. All right, so far so good? Okay. So let's look at what happens with the ionization energy. So if you take a look right here, first, after you remove the first electron, you got to go to IE2. Now for IE2, what do you notice the difference between the two right here? It's bigger, right? So does it mean it gets easier or harder to remove? Yeah, it's harder to remove the second electron. So let's make a note of that somewhere on the side. Okay, so it is harder to remove the second electron. All right, now, if you take a look at the next one, what do you notice about the next one? Yeah, it's higher, but do you notice that there's like a really big difference, right? The difference right here is about, what, 700? And then the difference right here is significantly more. It's more than 6,000, right? And so that's the observation that you need to make. The observation you need to make is that it gets even harder to remove the third electron. Okay? And it's not just a little bit harder, it is significantly more difficult. It's a massive jump in between IE1, IE2, and 2 and 3. Okay, so another way that we can write it is that the gap from IE2 to 3 is significantly bigger than the gap from 1 to 2. Yes?
Is it always going to be harder, like as you go down?
Yeah, it does get more difficult. We'll talk about why in a second, but and so what you want to look at is the significant jump. Where's the significant jump? So for example, just to kind of show you a different data set, if you look right here for aluminum, if you look at the data set, where's the big jump between them? Between what two numbers? 3 to 4. So it's going to be there's going to be a significant jump. It's just identifying where that significant jump is. Does that answer your question? Okay. All right. So let's talk about why these significant jumps exist, because that's what the question is asking us to do. So again, when you guys are doing the assignment, you guys don't need to draw the shell models, but it is very helpful to draw it. So I want to give you guys a minute, and I want you guys to draw magnesium's shell model. Okay, draw magnesium's shell model. All right, guys, so I got magnesium's shell model up there for you guys. It has 3 shells, 2 electrons in the first shell, 8 in the second, 2 on the third. Everybody good with that? Okay. All right, so let's take a look at what happens for all the ionization energies. Okay, so for the first ionization energy, what happens is you lose 1 electron, right? So IE1 is where you take away an electron. Now, if you take away an electron, you take it from the outside shell, right? So if I take away an electron from the outside shell, how many electrons are left in the outside shell? 1. So you're losing 1 electron, but there's still 1 left. So let's draw this one together. So we're going to write Mg, and if I lose an electron, it becomes +1. So we're drawing this together. After IE1, Mg becomes +1. And it still has 3 shells. Okay, we're going to ignore the inside shells for now because they didn't change. But the key thing to identify is that there's still 1 electron left in the outside shell. Okay. So I'll make a note right here. Regular magnesium had 2 valence electrons. But Mg plus, after IE1, it has 1 valence electron. All right, everybody understand that? That makes sense? Okay? All right, so that's IE1. Let's go to IE2 now. Okay, you're going to remove another electron. And if I remove an electron, how many electrons will be on the outside shell? Yeah, 0. So what happens to that shell? Yeah, it's going to disappear. And so after IE2, basically what IE2 does is it basically makes it lose the shell. So this is where you lose the outside shell. So Mg2 plus is going to only have 2 shells. And you didn't draw it on this one, but there's going to be 8 electrons in the new valence shell. Okay, so the key here is that there are now 2 shells, whereas the previous ones, there were 3 shells. Okay, so far so good? Making sense? It's stuff that we've done already where the shells disappear. Okay, so this is the one that we are interested in because I said we want to look at the jump that has the biggest difference in the numbers. We notice that IE3, the jump from 2 to 3, is so much bigger. Okay, if it is bigger, that means it is harder to remove. So that means that it is really hard to take away this electron compared to these ones right here. We were going to get rid of these ones in the previous, but it's really, really difficult to take away a 3rd electron. And that's the question why. Because if we're taking a 3rd electron, and you guys don't need to draw this one, but if we take away a 3rd one, we're taking away this electron in the 2nd shell, right? And I'm sure some of you guys can kind of tell why it's so much harder, okay? And it's because of the shells. Okay, so if we were going to write an explanation why, right here, this would be our explanation. Okay, for IE1 and 2, we are taking an electron away from the 3rd shell, right? So we would write for IE1 and 2, okay, the electron removed. Which shell was it in? Yeah, the 3rd shell. The electron removed was in the 3rd shell. So that's further away, right? But what about for IE3? Which shell is that electron in? Which shell is this electron in? The one that we need to take away now. The 2nd shell. For IE3, the electron removed is in the 2nd shell. Okay, and then you guys, based on what we learned already, it's harder to take an electron away if it's in a closer shell, because it's closer to the middle. Okay, and then so the conclusion is, okay, that electrons closer to the nucleus are harder to remove. Okay, and that is the reason why IE3 is so much bigger than IE1 and IE2. It's because you're not taking away from the 3rd shell anymore, you're taking it away from the 2nd shell. Okay? And so that is what you want to identify. And that's the type of questions on your assignment and on your exam for these multiple IEs. Okay, so just to help you guys visualize number 3, I have a shell model of aluminum. Okay, so we can help visualize it. So when we look at the data set, what do we notice about it? Where is that significant jump? Where's the significant ionization energy jump? 4, yeah. 4 is the one that's ridiculously big compared to the previous ones, right? Because first one to second, it's about 1,300, and then about 900, and then we got about like 8,000 something. Okay, so big jump between 3 and 4. So that's the one that we're really trying to explain right here. All right, so let's take a look at what happens in each of the ionization energies. Okay, for ionization energy 1, if you take away 1 electron, you will notice aluminum will still have 3 shells, right? So you're going to have 3 shells. IE2, you're going to take away a 2nd one, is still going to have 3 shells. But after the 3rd one, how many shells do we have for aluminum? Yeah, so 3rd one is where you take away a shell. So now you are at the 2nd shell. And so that means that IE4, what you are trying to do is you're trying to remove an electron from the 2nd shell. And that's the explanation for that big jump in ionization energy. It's because IE1, 2, and 3, you are taking away an electron from the 3rd shell, so it's further away. But for the 4th one, you are taking it away from the 2nd shell, which is much closer to the nucleus. So if I wrote that down as my explanation, I'd write something like this. Okay, so IE is going to erase from, okay, but then IE 4th shell. Okay, oh, sorry, not 4th shell, 2nd shell, my bad. 2nd shell is held tightly harder to remove. And that would be the explanation for why there's such a big jump. For IE 1, 2, and 3, you're taking away these three from the outside shell, which is relatively easy to do because they're further away. But once you try to do IE4, you try to remove that fourth electron, you start trying to take it away from one of the inside shell, which is much closer to the nucleus, and so it's going to be really hard to take away that fourth